A single clean energy plant, $30 billion over budget, 15 years late, and bankrupted the utility that built it. Nuclear power isn't dying from fear or radiation. It's dying because Western nations physically forgot how to forge heavy steel. To understand why clean energy stalled, we must dissect 4 systemic failures, starting with a hidden 15,000-ton press. To withstand 60 years of neutron bombardment, a reactor head must be forged from a single, seamless ingot of solid steel. Eliminating weld seams requires massive hydraulic presses. When Western nations abandoned heavy industry, we surrendered that metallurgical monopoly to Asia. When reactor construction halted for 30 years, an entire generation of master engineers, welders, and inspectors retired without passing down expertise. When Plant Vogtle broke ground, crews weren't just building a reactor. They were forced to relearn basic nuclear construction from scratch. Prefabricated modules built off-site arrived with tolerance errors measured in inches. This forced workers to demolish finished concrete walls to align steel frames. Miles of specialized safety wiring were installed, torn out, and reinstalled because initial blueprints weren't locked before concrete was poured. Logistics disintegrated into chaos. Millions of components sat in weather-exposed yards, losing their nuclear certification before ever reaching the reactor pit. As specialized suppliers went bankrupt or dropped certifications, sourcing simple safety-grade valves turned into a multi-year procurement nightmare. But losing supply chains was only half the nightmare, because while workers fought concrete in the mud, regulators kept moving the target. Unlike aircraft, where designs are locked before production, nuclear power plants suffer from a process called regulatory ratcheting. Midway through active construction, regulators mandated that active job sites redesign containment structures to withstand direct commercial aircraft impacts. Crews crammed thousands of extra tons of rebar into half-poured walls, creating steel density so tight that concrete aggregate couldn't flow evenly. Every added safety system forced a cascade. One backup component required 3 auxiliary support networks, multiplying physical complexity by orders of magnitude. Older reactors relied on active mechanical safety, meaning hundreds of redundant pumps and backup electrical networks, and required massive concrete protection. France successfully nuclearized its grid by building 56 identical standardized reactors. America built custom, bespoke cathedrals. Every utility hired different architects to build custom plants. America didn't build a standardized fleet. We built a series of unproven prototypes. Because no 2 plants shared identical blueprints, hard-won site lessons couldn't transfer. The industry's learning curve was repeatedly reset to 0. The results were disastrous. In South Carolina, $9 billion was spent on the VC Summer plant before the entire build was completely abandoned mid-construction. $9 billion of ratepayer money vanished into thin air, leaving behind empty concrete pits and abandoned steel structures. Georgia's Plant Vogtle reached completion, but only after its price tag surged from $14 billion to over $35 billion. Utilities poured concrete when designs were only 30% complete, guaranteeing that future design changes would require demolishing finished work. But rework was only fuel for a far more dangerous engine. The true killer of nuclear energy isn't concrete, steel, or uranium fuel. It is a mathematical trap called interest during construction. Every single day of delay compounds project debt exponentially. And when a multi-billion-dollar loan sits idle for 15 years, the cost of time alone becomes larger than the physical power plant itself. Uranium fuel has incredible energy density. A single pellet holds the energy of 1 ton of coal. But using it requires surviving bank interest first. Nuclear reactors require massive upfront capital. Utilities must borrow billions before generating a single kilowatt of electricity. If a plant opens in 5 years, loan interest is manageable and easily paid off through future electricity sales. But when delays push construction out to 15 years, compound interest accumulates every second, even while work is stopped for audits. At peak delay, simply keeping the lights on and servicing loan debt at an idle nuclear construction site costs over $2 million every day. On Georgia's Vogel project, over $12 billion of the final price tag was nothing more than interest paid on loans during delays. Nuclear reactors require massive upfront capital. Utilities must borrow billions before generating a single kilowatt of electricity. Without explicit government loan guarantees, private capital refuses to fund traditional nuclear builds. The risk of delay means utility bankruptcy. This created a vicious decay loop. High costs stopped orders. Lack of orders destroyed supply chains, making future builds twice as expensive. When energy markets deregulated in the 1990s, high upfront cost nuclear plants could no longer compete with cheap fossil fuel spot pricing. We trapped ourselves by building gargantuan monoliths, designs so large that a single mistake could sink an entire utility company. Wall Street saw this financial death spiral and fled. A natural gas plant builds in 24 months for a fraction of the cost, yielding fast returns. The financial weight was so crushing that even legacy nuclear manufacturing giants like Westinghouse were forced into Chapter 11 bankruptcy.
To escape this financial trap, engineers realized they had to fix the safety architecture first, by replacing mechanical pumps with pure physics. Legacy reactors relied on active safety. If station power was cut, mechanical pumps stopped moving water, requiring diesel backup generators.
In older designs like Chernobyl's RBMK, steam bubbles increased reactivity, creating a positive feedback loop that could destroy a core in seconds. At Fukushima in 2011, the reactors survived the earthquake. But when tsunami waters flooded backup generators, cooling pumps failed completely. These disasters forced engineers to eliminate human reliance entirely. Gen 3 Plus designs feature massive water tanks built directly into the containment roof. If power fails, gravity drops cooling water onto the inner steel shell automatically. Natural convection cools the core for 72 hours with zero electricity. By letting gravity and natural circulation replace electric motors, passive safety eliminated thousands of moving parts and failure points. Fewer pumps and backup generators meant containment buildings could shrink significantly, reducing the required volume of safety-grade concrete. Passive safety was a massive engineering leap, but it didn't solve the core financial problem. Plants were still too large to build off-site. They were still constructed outdoors in the mud. To defeat the interest trap, engineers made one final paradigm shift. Stop building reactors like custom megastructures and start manufacturing them on an automated factory assembly line. Small modular reactors replace outdoor construction sites with factory assembly lines, building components with millimeter-level precision. Instead of forging giant multi-piece structures on-site, complete SMR reactor vessels are manufactured in factories and shipped directly by rail. Instead of borrowing $30 billion for one megaplant, utilities can install $1 billion SMR module in 2 years. Module 1 generates immediate electricity revenue to self-finance subsequent modules, completely neutralizing the compound interest trap. Automated robotic welding and standardized factory testing eliminate the field welding errors and inspection delays that killed mega builds. SMRs allow utilities to deploy clean baseload power incrementally, without risking corporate bankruptcy on a single multi-decade build. Nuclear power was never killed by its physics. It was crushed by lost manufacturing, broken logistics, and compound interest. When you fix the manufacturing, you fix the economics. And when you fix the economics, clean nuclear energy becomes unstoppable. If you want to see how we dissect the world's most extreme engineering challenges, hit subscribe.